Greetings, sir. I'm Yashaswini C. from the Department of Chemical Engineering. Today I'll be presenting on thermodynamics engineering. My topic covers some of the most important concepts from the second law of thermodynamics, that is, Carnot cycle, heat engine, refrigerator and heat pump, Clausius inequality, entropy, and some solved problems. The Carnot cycle. The Carnot cycle was proposed by Nicholas Leonard Sadi Carnot in 1824. It is an ideal reversible cycle that operates between two temperature reservoirs and gives the maximum theoretical efficiency for any heat engine. The working principle is based on the second law of thermodynamics. It consists of four reversible processes. Two are isothermal processes where temperature remains constant, and two are adiabatic processes where no heat exchange takes place. The working substance, such as an ideal gas, undergoes all these four stages to complete one cycle. Now let's know the four processes in Carnot cycle, which is also represented by pressure versus volume diagram. The four processes are 1. Isothermal expansion. Gas absorbs heat from the hot reservoir and expands. 2. Adiabatic expansion. Gas continues to expand without heat exchange and temperature drops. 3. Isothermal compression. Gas is compressed, releasing heat to the cold reservoir. 4. Adiabatic compression. Gas returns to its initial state without heat exchange. Here we can see the PV diagram of the Carnot cycle. The efficiency of the Carnot cycle depends on the temperatures of the reservoir. It is given by eta is equal to 1 minus temperature of cold divided by temperature of hot, which means higher temperature difference gives better efficiency. Next we have heat engine. Heat engine is a device that converts heat energy into mechanical work. It works in a cyclic process between a hot reservoir and a cold reservoir. And the components of heat engine are hot reservoir. It provides heat such as a boiler or furnace. Next is working substance, usually a gas or vapor that absorbs heat, expands and performs work. Cold reservoir, it receives the rejected heat like a condenser or cooling water. Next, piston or turbine. It converts expansion of the working substance into useful work. Efficiency of a heat engine is given by eta is equal to 1 minus Q2 divided by Q1, where Q1 is heat absorbed and Q2 is heat rejected. Next, we have refrigerator and heat pumps. A refrigerator removes heat from a low temperature region and rejects it to a high temperature region by consuming external work. Its process is to keep a space cool, like in refrigerators or air conditioners. A heat pump works in the reverse way. It extracts heat from a cold region and delivers it to a hot region, used in room heaters or water heaters. Both of them operate on the reverse Carnot cycle, meaning they use mechanical work to transfer heat against its natural direction, from cold to hot. Now we'll talk about Clausius inequality. The Clausius inequality is a mathematical expression of the second law of thermodynamics. It states that for any cyclic process, the sum of heat exchanges divided by the absolute temperature is always less than or equal to zero. This inequality helps to express the second law mathematically, differentiate reversible and irreversible processes, and form the basis for calculating entropy. Now we have entropy. Entropy is a thermodynamic property that measures the degree of disorder or randomness in a system. It was introduced by Rudolf Clausius in 1865. Entropy is denoted by S and measured in joules per Kelvin. For a reversible process, the change in entropy is given by delta S is equal to Q reversible divided by T. Entropy helps us understand how energy spreads and why some processes are irreversible. Here we'll find the entropy change for common processes. Isothermal process, for ideal gas, T is constant. So delta S is equal to N R natural log of V2 by V1, which is also equal to Nc natural log of V2 by V1 for ideal gas, where N is the number of moles, V1, V2 is the initial and final volumes, and R is the universal gas constant. For isobaric process for constant pressure, entropy change is delta S is equal to Ncp natural log of T2 by T1, where Cp is the specific heat at constant pressure. For isochoric process for constant volume, entropy change is delta S is equal to Ncv natural log of T2 by T1, where Cv is the specific heat at constant volume. So here I've included two example problems to show how entropy change can be calculated using different formulas depending on what data we have. In the first case, I'll read out the question. Calculate the entropy change when 10 moles of an ideal gas expands reversibly and isothermally from an initial volume of 10 liter to 100 liter at 300 K. Here we are given the volumes. The process is isothermal and reversible. So we use the formula delta S is equal to 2.303 nR log V2 by V1. After substituting 10 moles, R is equal to 8.314 joules per mole Kelvin and volume ratio 100 by 10, which is 10. We get delta S is equal to 191.47 joules per Kelvin. Then I mentioned another type of problem where instead of volume, we are given heat or latent heat. I'll read the question. Suppose 0.1 kg ice at 0 degree Celsius, that is 273 Kelvin, is in 0.5 kg water at 20 degree Celsius, that is 293 Kelvin. What is the change in entropy of the ice as it melts at 0 degree Celsius? Latent heat of fusion is 3.33 into 10 power 5 joules per kg. In that case, we use delta S is equal to Q by T or ml by T for phase change processes. For example, when 0.1 kg of ice melts at 0 degree Celsius, we use delta S is equal to ml by T, which is equal to 0.1 into 333550 divided by 273, which is 122.18 joules per Kelvin. So here the entropy change is positive because the ice absorbs heat and becomes liquid. This comparison shows how the formula depends on the information. If we know heat, we use Q by T. If we know initial and final volumes, we use nR log of V2 by V1. So my slide shows both the conceptual difference and numeric application. Thank you.